Upon entering the first prepupal stage, the larval body shortens and becomes immobile. Movement of larval mouth hooks and the pumping dorsal vessel or heart can be seen. This stage, called the white pupa, is ideal for studying heartbeat. The dorsal vessel you see beating is pumping blood or hemolymph through an open circulatory system. In the background, you are hearing the sound of the heartbeat electronically translated from an optical recording. Later in metamorphosis, the heart will stop beating as tissues are reorganized.
These real-time sequences show blood flow and a beating heart in a tadpole, Xenopus.
You are looking at a single adult rat heart cell, isolated and growing in culture. The cell is approximately 120 micrometers in diameter. Heart cells are specialized to beat, and individual cultured cells will beat at different frequencies. It is only when these cells are connected to each other that their beating becomes synchronized. This cell is cultured not on glass, but on a thin, flexible silicone rubber substratum that wrinkles as the cell contracts. These wrinkles are a visual indication of the forces this cell is exerting on its extracellular world. Normally, in an intact heart, the forces are transmitted from cell to cell, maximizing the effectiveness of the heart as a pump. This is another heart cell beating on silicone rubber. Note that adult rat heart cells are binucleate. This cell was injected with fluorescently labeled alpha-actinin, which is a major protein in the Z-bands of the myofibrils. When we shift to fluorescence microscopy, you will see the Z-bands as short, parallel white lines, which are especially prominent near the margins of the cell. As myofibrils contract, the Z-bands move closer together due to the interaction of actin and myosin. This is a time-lapsed sequence of a region of the yolk sac of an embryonic killifish that is about 2 days old. The field of view is approximately 250 micrometers in diameter. In this region of the embryo, you can see a large black pigment cell, many migratory deep cells, and the beginnings of blood vessels formed by endothelial cells. These blood vessels must form in a carefully coordinated manner throughout the entire embryo to ensure a closed circulatory system. As you watch, you can see the very first blood cells to be pumped through these vessels. A small group of blood cells appear to get stuck in an unfinished blood vessel in the center of the screen. The endothelial cells remodel and the vessel opens up. Unlike the more mature, flattened blood cells you saw in the opening sequences of this video, these very young embryonic blood cells are rounded and often bleb. The time compression is 1 to 85. As we switch recording speeds so that events appear to happen much closer to real time, we see that the blood cells are actually slowly progressing through the blood vessels as the young heart just starts to pump. When we switch back to the original recording speed, the dynamics of blood cell movement become obvious.